change of coordinate matrices actually affect both vectors and linear transformations, but they affect a particular kind of linear transformation. So here's the definition. A linear operator is a linear transformation, T from V to V, from a vector space to itself. Okay, those are linear operators. And so we have a theorem about change of coordinate matrices and how they interact with linear operators. Let T be a linear operator, and let beta and beta prime be two finite ordered bases of V. If Q is the change of basis matrix from beta prime to beta, then the matrix representation of T in terms of beta prime is equal to Q inverse, remember change of basis matrices are invertible, times the matrix representation of T in terms of beta times Q. Okay? Now this proof sort of centers on remembering some basic facts about what's going on. First fact, you'd be up a creek if you didn't remember how you get a change of basis matrix. Remember, it's the identity map on V, but represented from basis vectors in terms of beta prime to beta, okay? Now, we know that any transformation T is equal to the identity map composed with T, or T composed with the identity map, right? I mean, that sort of goes without saying. Doing nothing and then T is the same as T, okay? But that means if this is two different ways of representing the same map, then the matrix representation of this should be the same in both directions, okay? So I want to start with beta prime and go to beta, beta prime, beta. Okay? And remember, matrix representation of linear transformations decomposes across composition of linear transformations. So let's see, if we start at beta and stay in beta, start in beta prime and then go beta prime to beta, that's the same thing as having IV going from beta prime to beta, and then T in terms of beta. So notice this starts in beta prime, goes to beta, stays in beta. Stays in beta prime, goes from beta prime to beta. So they both did the same thing. But notice that and that, those are Q, right? That's exactly Q. And of course, if you want to get this result up here, you multiply by Q inverse on the left, and you get this result. And frankly, you can notice that if you wanted to, you could multiply by Q inverse on the right, and you could get back the other direction. So this is the proof, but you can get back and forth. There's also a definition that's worth sharing here, and it's the definition that ends this section. These two matrices, those are called similar matrices. And in general, if A and B are n by n matrices, we say that B is similar to A if there exists an invertible matrix Q such that B equals Q inverse A Q, okay? And incidentally, this is an equivalence relation. Obviously, A is always related to A. Obviously, if B is related to A, you could just put Q inverse on the other side, and A is related to B. And if A is related to B and B is related to C, then A is related to C.